Hello and welcome. In this video we'll be looking at how to use NumPy and SciPy inside a Jupyter Notebook to repeat the simple optimization problem that we looked at last time, but we're going to loop over a grid of parameter values. So just to recall, we were looking previously at a wine aging problem. So the problem here in finance is to maximize the present value of wealth subject to a production function. So that is the production function there. Technically a storage function, since this is just about storing wine to age, but it's the same as a production function that describes part of a circle. And there's no borrowing here, so the wine merchant just has to decide how much wine to store, and that determines how much wine is available in the second period according to this curve. And we're going to be looking at a range of interest rates from 1% to 20%. This is what we call in economics an example of comparative statics. So we're really defining demands here for wine in each period. You can think of it that the firm's or output and input decisions, depending on how you want to think about it. I'm not really going to worry about those technical details and the signs of whether things are inputs or output right now. But what we want to do is be able to look at how those choices, the K1 and K2, respond to changes in the interest rate. And that's a classic example of comparative statics, or what in engineering or mathematics might be called sensitivity analysis. So it's really about examining how behavior changes with change in exogenous or external parameters, and that's the kind of thing one wants to do over and over again in many economic, social science, behavioral, or business contexts. So the first thing to do is just to break writing our code down into components so that we can check that we get the right answer. You could do all of this in one big go, and as one gets more experience, that's probably fine, but I just want to break it down here into steps so that we can see what's happening. And we're going to start off with just an interest rate of 6% to start off with, so we can check that our code is running before we iterate. So the first thing we're going to do is define a function which is our objective. So it's about maximizing the present value of wealth. However, because the optimization command we're going to use is a minimization one, we need to take the negative of the present value. So we've called that here neg present value of wealth, which will depend on the choices, x's that we put in each period, and r, the interest rate. So in particular, in the first period, it's just going to be minus the appropriate x, and in the second period, that's going to need to be discounted back by 1 plus r, and then we've got the negatives in front. And then we can just pop in a couple of values to check that that is working correctly. So let's just comment those out to start with and just check that our definition, yep, that worked okay, so we didn't have any problems with the definition. Now let's define an array. We could just pass this directly, but we need to actually load our libraries that we're doing. And now let's define that array again. So we've defined an array of 10 and 10. And then let's calculate the negative of the present value, and with an interest rate of 0.6, so a 60% interest rate. So a very high interest rate, which is why this number is so far from 20, because with 10 and 10, with no discount, we'd get minus 20, so we get minus 16 here, and that's because the discounting is so very strong. If we wanted to redo that with no discounting, then we get out minus 20, of course, because it's just the sum of the 10 and the 10 in each period times minus 1. So we'll just put that back. If you want to get help with the optimize package, remember you can just put in opt.minimize, that's the particular command we're going to be using, question mark, and it'll pop up the help for us. Alright, let's look at the full problem here. So we're going to initially set the interest rate to be 6%. We already have our objective function here, which is to do with the present value of wealth. We need to pass some initial values to the optimization function, so we're just going to give it 10, 10, and we need to define the constraints. So this is a dictionary command here, so it's paired, so the type is an equality problem, so we need to be on the constraint, and the function which describes that constraint is defined anonymously using the lambda. X maps to x0 squared plus x1 squared minus 100. So that's basically this curve here rewritten in the standard way we write constraints, so all the numbers over on the left hand side. And then finally we pass all that information to the optimization command. Here, because we're using r at 0.6 rather than putting 0.6 directly into the function, we have to pass that argument to the minimization function as well. And so this is a little extension of what we did before. Previously we were just passing choice variables with their initial values to the function, and we weren't solving at parameterized values of the function. So back up here there was an r. So we're not searching over that r, but in order to be able to evaluate the function, Python needs to know what r is. It's 0.6, and we need to tell it that here to go and look for that value of r. And then we should print the outcome. So let's run that, and we get the answer that we would get rounded to 2 decimal places if we performed this by the method of Lagrange multipliers. So that all seems to be working fine. Now what we want to do is loop over a grid of values. So this is where we want to see how those choices vary as we vary the interest rate R from 1% to 20%. Now, if we were given some particular values of the interest rate we wanted to check, we might put those particular values in an array. But we really just wanted to look at the behavior here. So let's just look at evenly spaced points over that range. And so the NumPy command linspace does that. It linearly spaces them out. So starting value at, that should be 0.01 up to 0.2, so that's 1% up to 20%, and we're going to do that in steps of 20. So those are our interest rates, and then we'll just print it to check that we've produced the right thing. So there's our array starting off at 0.01, 0.02, so 1%, 2%, all the way up to 20%. So that is our interest rates that we're going to loop over, and those are stored in an array called iRates, for short for interest rates. Now we're going to be interested in these k demands, so let's just initialize our array there. So we'll put all zeros in, and we're going to have 20 iterations, and we're going to be getting 2 results for each of those iterations, so a 20 by 2. And so we will also just check that should be all zeros, which it is. Right. Remember, we have to do this initialization, otherwise when we call something inside the loop that we haven't defined previously, we will end up with an error message. Standard stuff now for the minimization problem. We need to give it some initial values. We actually defined these before, but let's just define them again for concreteness, and we need to set up the constraints using the dictionary. So the brackets here are just kind of saying it's a function. The curly brackets, the braces here, are the symbol for a dictionary, and so the dictionary here is 2 things. Type is equal to maps to EQ for equality, and function maps to that lambda defined constraint, which was the production function. So that's just the same as before, and we're all ready to go. So let's have a look at the loop. So we're going to run a for loop, which I like to use because we know exactly what's going on. So we're going to make up a variable called index, which we're going to use to run through the steps in the loop. And now, how many times do we want to run through the loop? Well, it depends on the number of interest rates that we have set up. So len is going to calculate the length of that array interest rates, so that tells us how many we've got, and so that's going to be a number, 20 in our case. And then range 20 will set up the integer counters that we will run over in the standard kind of the way. We didn't really need to do this because we know it was the number 20, so we could just substitute in the number 20. But this produces nice code that we would only have to adjust in one place if we wanted to change the number of iterations. So if we wanted to change, sorry, in two places, if we wanted to change the number of times we were going to, or how fine the grid was, the number of times we're going to iterate, we would have to change this number here, this 20, and we would have to change this number here. We could in fact actually make that a variable as well, and then we'd only have to change it once. But we don't have to change it down here in the loop. So what are we going to do in the loop? Well, we calculate the demands, as we're calling them, which are minimizing the present value of wealth at some starting point for a given value of the interest rate. So now interest rate is an array, and so we were pulling out the value of the interest rate that corresponds to this value of index. So we start off with the first, the second, the third, and so on, and of course subject to the constraints. We get two values out here, x0 and x1, and we're going to put those into the corresponding row, the first place in the row and the second place in the row, working through the index, so that we get a different row each time that we run through. We could do this all in one go and pass it two objects and fill up the row in one go, but let's just break it down into steps, and then finally let's print out those results. And here they are. So starting at 1%, 2%, 3, 4, 5, 6. So this one should be the same as what we got before if I've highlighted the right row. And as you can see, as the interest rate goes up, this column here, which is the amount in the first period, goes up, and this column here, the amount in the second period, goes down. Now, this is a prime example of why visualization is useful. We wasn't required in the question that we were initially looking at. We were just looking for the answers, but the answers are a bit hard to see what's going on. So it's a great time to just draw a line graph of the results and see what the curves look like. And so we can do that here with the matplot library. So we import matplot as plt plot. So first up, and remember, often you can get away with not putting all these commands in, but let's do it every step. So we set up a figure, and we populate that figure with some axes, which we're going to call axis 1, x1. There's going to be just 1 by 1, so there's just one axis, and we're going to work with that first axis. So that's what those three elements are. First of all, we use the method plot, which is a line graph joining up individual points, and we apply that to axis 1. On the x, we're going to have the interest rates, and on the y, we're going to have the k demands, and we're going to take the first period, and we're going to mark those with a 0 so we can tell them apart, or a solid dot. And then we're going to add another line plot to this same axis, again common interest rate on the x-axis so that it makes sense, and we're going to put in the demands, as we're calling them, in the second period and mark those with a cross so that we can tell them apart. Let's add a title to the plot, wine quantities per period. The y-axis is the quantity of wine, and the x label, that's the x-axis label, is the interest rate. And then finally we show the plot. And there we go. So we can see one sloping up and one sloping down. So that's a much nicer way to be able to visualize it. We can see that those are looking like straight lines there. It's rather hard to tell things like curvature and distance between things from looking at the table of numbers here. And if we think about it, it sounds right that these things should be converging, because at a zero interest rate, it would be you could just allocate optimally between you could just allocate evenly between periods. And it wouldn't make any difference. As the interest rate gets bigger and bigger, then the differences between the periods get more and more pronounced. So that's nice to be able to do a quick visualization to interpret the results. So that really is a template for how we might do all kinds of problems, either using Monte Carlo methods or numerical optimization, or some combination. We can tackle all kinds of problems in economics and finance and then visualize the results to understand the relationships that we're investigating a little bit better. And so that concludes today's video.